Welcome to Algebra 2, Unit 1, Section 2, Function Concepts. Before I've had my coffee, I can't grasp any concept of functioning, period. It's an old person joke. You'll get it someday. After this lesson, you will be able to identify the difference between discrete, continuous, and discontinuous functions. Okay, a discrete function is a relation where the domain consists of individual elements and the graph is unconnected points. So basically, it just looks like this. Just points on a graph. All right, they're just all separate values and they're unconnected. Okay, so now we're going to talk about continuous functions. Continuous function is a relation or a function which the domain has an infinite number of elements and the graph is a connected line or smooth curve. So if we have a line such as this, right, that would be considered a continuous function. A parabola would also be considered a continuous function. We could also have a curve, right? We could also have a curve, all right? Curved function like this. That would be also considered continuous, all right? You'll notice that each one of these has arrowheads on the ends of their respective graphs, right? That means they go on for infinity, right? That's thus this infinite number of elements. So that's important. It's got to continue. Discontinuous functions, that's a function where the line or curve breaks at any point, creating either a hole or what we would call an asymptote in the graph. So a hole is often represented, let's say we have a parabola, we're going to start here, and there's a little circle there that represents a hole in the graph. Now, the other thing that might happen with this is we might have another point right here at that x value. Okay, that is still a discontinuous function. Okay, this is what, like I said, we have a hole in the function. Okay, the other types of discontinuous functions that we may have is with a break. So with a break in the function, I might have something that's going along such as this, and I might have a dot at the end of this, and then I've got a break here and I've got a circle here, and I might go like this here. Okay, so we have this gap, right? There's a gap there. Okay, so that is also a discontinuous function. Now an asymptote is a thing that occurs within a graph where we are coming very close to a value, but we don't touch it. So we might have something that looks somewhat like this. And what this asymptote here would be that it gets really close to this x value here, but it doesn't touch it. And this is what's called a asymptote here. So this is a vertical asymptote. This is a horizontal asymptote. asymptote. And this other side of this graph, it could look like this, right? And come real close here, and then go down to this one. It could also be, the other side of the graph could look like this, okay? So that's typically what they look like, these type of curves that get really close to values. And we're going to explore that later. All right, so let's take a look at this relation. Determine if this relation is discrete, continuous, or discontinuous, and explain why. Go. Now, as we look at this function, we can see we come to this point here, and then we have this hole down here, and then we continue this function this way. So it is not continuous, right? So we can cross that one off the list. And it's not a bunch of points, so it's discontinuous. And why? Because there is a gap in the graph. Let's put the word graph down there, that's important. In the graph of the function. Okay, look at this one. Decide whether it's discrete, continuous, or discontinuous, and explain why. Well, we can see here that this graph is not discrete, and there's no gaps, so it is continuous. Why? No holes or gaps. Okay, do this one. Well, we can see right off the bat, this is not continuous. It's a bunch of dots, which means it's just what? Discrete. All right. So separate graphed points. That's why. All right, do this one. Well, we can see right off the bat, not discrete, not continuous, so it's discontinuous. Why? Well, again, we talked about this. It has, right, vertical asymptote. A horizontal asymptote will not cause a function or a relation to be discontinuous, but a vertical one does. All right, let's discuss function mappings now. So this function mapping is called a one-to-one function mapping, that each element in the domain maps exactly to one element of the range. It doesn't matter if there's more elements in the range that are not being mapped to. All that matters is that each function in the domain only maps out to one element in the range. So this is called onto, and each element in the range corresponds with an element in the domain. So you'll see here 1 matches up to A, 2 to B, 3 to C, but 4 also matches up to B. So there are 2 values in the domain that match up to 1 value in the range. That's called onto. Okay, so here's both 1-to-1 and onto. So in this instance, there's an identical number of values in the domain, and they match up to the identical number of values in the range. So you'll see there's 4 values in the domain, and there are 4 values in the range. So they match, and they all match up 1-to-1. Okay, determine if the function is 1-to-1, onto, or both, or neither. Justify your answer. All right, so let's go through the process that we would use here. So Jalen, we have matches up to Village Grinder. Keisha goes to Zen. Carson goes to Hardee's. And Tommy goes to Stories. There are an identical number, right, of items in both the domain and range, right? So we have 4 here to 4 here. They match up 1-to-1. So this is both, right? And the reason it's both is it's 1-to-1 with same number of elements in the domain and the range. All right, figure this one out. Okay, so as we look at our map, we can see here that we have 2 values, even though they have the same number, right? They both have 4. But Jalen goes to Village Grinder, right? Tommy goes to Stories. But these 2 here go to Zen Coffee. Hardee's is not included in the function. So this would be onto, right? And this is because 2 values, 2 domain values go to 1 range value. Okay, match this one up. Okay, this problem is very similar to the one we used in our example of what this is. So Jalen goes to Village Grinder, Carson goes to Hardee's, and Keisha is at Zen Coffee. This is a 1-to-1, right? Because even though there's more values in the range, it's 1-to-1. Nothing's doubled up, all right? So 1 domain, to one range value. Okay, go to work. Okay, we can see here that we're going to end up with two values from the domain that end up on the same value in the range. Okay, so due to this, we're with onto, right? So two domain values have the same range value.